Hi, good morning. My name is Maria. I'm working in Astrobiology Center in Madrid, Spain, and I'm doing my PhD there. My studies, my research is about amino acids on different surfaces, and I use different spectroscopy and microscopy techniques. In this talk, I'm going to show you a comparison of amino acids reactivity of minerals in opposition to metal surfaces. Okay, the main objective of my study is try to explain how the simple organic and inorganic molecules, like amino acids or gases, through chemical reaction and possible catalyze, become complex organic molecules. The amino acids and metal ions are present in the nature in different places. Could arrive to the Earth from the meteorites. The meteorites are rich source of amino acids and metal ions like nickel, iron, magnesium, and they are present too in hydrothermal systems. And the chemical interaction of amino acids with metal ions is essential in many biological processes. For example, metalloproteins, hemoglobin, or hemocyanin. The amino acids are the biological building blocks, and they are essential for the formation of the proteins, and they have an important role in molecular biology, medicine, and biochemistry. They provide two different functional groups, acid group and amino group, and some amino acids also have additional reactive groups like sulfur or aromatic rings. Their chemical forms can be neutral, anionic, cationic, or deuterionic chemical form. The anionic chemical form has amino group and carboxylate group. The cationic chemical form has a protonate amino group and acid group. And deuterionic chemical form has a protonate amino group and carboxylate group. In my experiment, I have using cysteine amino acid. Cysteine is the dimer of the amino acid cysteine, and it has two cysteine covalently linked to make a disulfide bond. And it has 5 reactive groups, 2 acid group and 2 amino group. And it has a disulfide bond. In my experiment, I have used 3 different surfaces. 2 metal surfaces, they are gold and copper, and 1 mineral surface. It is pyrite mineral, and all them, they are single crystal. Several theories have proposed the mineral as a possible site for absorption of amino acids, and some amino acids are very strongly absorbed by some mineral surfaces. This absorption could have facilitated peptide formation by increasing the effective concentration of amino acid and catalytic sites on the surface. Minerals like silicates, oxides, and sulfides have been present on the early Earth. Pyrite is the most important sulfide mineral on Earth, and many chemical, geochemical, and biological reactions occur on its surface. It is present in many redox-based geochemical and biogeochemical processes and in deposit formation. This is my laboratory. In my laboratory, I work in this chamber. We have 2 different chambers with ultra-high vacuum conditions. In this chamber, I have the cleaning processes. I have sputtering and annealing to clean the surface, and I have XPS technique. And the other chamber, I have LEED. LEED is low energy electron diffraction, and STM, scanning tunneling microscopy. And why I need ultra-high vacuum conditions? Because with this condition, I get a clean condition and in-depth control of the experimental parameters. And my techniques require ultra-high vacuum. With ultra-high vacuum allows us to study the atomic level, and it is possible the study of monolayers. In this experiment, I have using XPS. XPS is X-ray photoelectron spectroscopy, and it's a surface characterization technique. With this technique, I can get information about elemental composition, chemical state, electronic structure, and the stoichiometry of the sample under study. Here, you can see the overview XPS spectra of the pyrite mineral single crystal, and we can observe the different regions of the pyrite: the iron region, the oxygen region, and the sulfur region. And there are Auger peaks too, but in my experiment I study only the XPS peaks. So the summary of objectives are to understand how amino acids interact on surfaces, to evaluate the role of the surface, to demonstrate that surface is more reactive and better as catalyst, and to study of absorption of amino acids on surfaces by innovative and complementary surface techniques in the astrobiology field. About the result, with XPS, I can study the different regions of the amino acids and the surface. In my amino acid, I have carbon, oxygen, neutron, and neutron region. And in pyrite, I have sulfur region. I'm going to start with the carbon region. In this slide, you can observe the XPS photoemission spectra of carbon 1s core level peaks of cysteine absorbed from gas phase on the gold, copper, and pyrite surfaces. And for the three surfaces, two components are observed. The higher binding energy component is a carboxylate or acid group. The other component is carbon joined to amino group and carbon joined to disulfide bridge. In the oxygen region, we can observe some difference between the metals and the mineral surfaces. In gold surface and copper surface, we can observe only one component. This component is carboxylate group. The acid group is desprotonate on copper and gold. And on pyrite, we can observe two components, the carboxylate group and the acid group. And the other component is the component of natural pyrite, but is not oxygen. And about the nitrogen region, we observe difference between the surfaces. When the amino acids are absorbed on the gold surface, we have only one component, and it's protonate amino group. When the amino acid is absorbed on a copper surface, we have only one component, and is amino group. And on pyrite, we can observe both components, amino group and protonate amino group. And about the sulfur region, on pyrite surface, we have two components too. The main component is the disulfide iron of the natural pyrite, and the other component is polysulfide present in the natural pyrite. And on copper and gold surface, I have similar spectra, XPS spectra, and I have two components. This component is is to metal, disulfide metal component. And this component indicates that the molecule is interacting on the surface through a disulfide bridge. And the other component is the disulfide bridge, and this component indicates the molecule is not breaking when it's absorbed on the surface. Okay, here we have a summary of the binding energy of the different regions, carbon region, oxygen region, and nitrogen region. And oxygen 1s and nitrogen 1s region present the most significant difference. With oxygen and nitrogen region, I can know about the chemical form of the molecule. For example, I know the amino acid on gold The chemical 4 is switterionic because I have carboxylate and a protonate amino group. On copper, the chemical 4 of the amino acids is anion because I observe the carboxylate and the amino group. And on pyrite, we observe two chemical forms, anion and cation, because we have a carboxylate and acid group, and amino group, and protonate amino group. So the conclusions are, cysteine molecule has been successfully absorbed on gold, copper, and pyrite. There is 3 possible interaction points of the molecule on the surface, disulfide bridge, carboxylate group, and protonate amino group. And chemical form of the molecule absorbed depends on the reactivity of the surface. And pyrite is more reactivity than copper and gold. Because on pyrite, I can observe 2 different chemical forms, anion and cation. While on copper and on gold, I observe only 1 chemical form. On gold is switterionic, and on copper is anion. Therefore, pyrite could be a good candidate to absorb amino acid and to facilitate the peptide formation. Thank you very much.
Hi. I was wondering whether you believe that the disulfide bond formation, whether that's catalyzed by the surface of the metal through a specific chemical interaction, or whether it might just be from a decrease in the number of degrees of diffusional freedom.
Maybe the mineral or the surface has a catalytic site, and when the mineral or the metal absorb of amino acid, this amino acid could get to form a protein in the specific sites.
Just to clarify, all these reactions were happening in the gaseous phase, that the amino acids were sent in the gaseous phase and then they were absorbed on the mineral surface?
Okay, I have done different studies.
Okay.
In my laboratory, I study the experiment from solution and from gas phase. In this talk, I speak about the from solution. And for this experiment, I have a special transfer, and I put my molecule there, and I heat it, and I evaporate the molecule inside of the chamber. Right. And when I do the experiment from solution, I take my surfaces, and I put the surfaces in a solution of the amino acid with molecule water. Mm-hmm. And then I transfer to the chamber, and I use the different techniques to do a comparison.
So you did both gas and water for all 3 minerals?
Sorry?
You did gas and the solution experiments for all 3 minerals, gold, copper, and pyrite?
No. I am working from solution on gold. Okay. And on pyrite. But okay. The difference is when it's from solution, it's not necessary single crystal, it's polycrystal. Okay. But in ultra high vacuum, I need single crystal because with this technique LEED and STM, I need a crystallographic extractor.
All right. Finally, what was the rationale behind using these 3 surfaces, gold, copper, and pyrite?
Sorry?
What was the rationale, as in why these 3 solid surfaces?
Okay. I start with metals because metals are inert. They are ideal condition. Mm-hmm. And I want to compare it with pyrite because I am working in astrobiology center, and we try to explain the minerals like possible catalysts. There are some theories, Bernal, and I don't remember the name. It's German.
That's what I wanted to know. All right.
About
okay.
the mineral.
I see what you mean, yeah. All right. Yeah, thanks.
Thank you.